for this particular problem, okay, what is it? For this particular problem, we have 3 blocks, okay? Now, before we talk about any of the calculations here, I actually want to give you another question, but let me go ahead and draw this picture first. So you apply a force that's 12 newtons, 1 kilogram, 2 kilograms, and 3 kilograms, all right? Are we good with the picture? Okay? Now, if you're good with the picture, could you also draw another picture right above the question? But in this case, we will only draw 1 block. Okay, we'll only draw 1 block, and we also have 12 newtons of force. But in this case, the block is going to be 6 kilograms. Okay, just 1 block of 6 kilograms. Now, for the picture above, okay, let me zoom in. You've got the mass. You've got the force. What can you give me? Acceleration. Could you go ahead and find out the acceleration of this block? Again, there's no friction on this surface. Can you find out the acceleration of this block, this 6 kilogram block? It will be 2, because F is equal to MA, right? Or net force is equal to MA, and we have 12 newtons equals to 6 kilogram times A. So 12 divided by 6, it is 2 meters per second square. Are we good? Yes? All right, now, if we're good, let's go back to the picture down below and my illustrations for you in front of you here. If I am pushing, okay, these 3 blocks, do these blocks have the same acceleration or different acceleration? Okay, again, if you're going to push from one end and these 3 blocks are moving, right? Do they have the same acceleration or do they have different acceleration individually? What do you think? Same or different? You think different? You think different? Now, if you say different, then we have a little bit of a weird situation. If you say they're different, that means some of them will go faster than the other. Do they? They go together. That means they are sharing the acceleration. They all have the same acceleration. They all have the same initial velocity. They all have the same final velocity. Right? Yeah. I'm recording this video because I want to make sure that people can watch it at home. So if you have trouble understanding this scenario, you can simply find 3 objects that can be pushed along the surface. And you think about how, if you push these 3 objects together, they move together, right? They move together. So they all share the same acceleration. It would be strange that they have a different acceleration individually. Okay, so it's tempting. Now, let me guess. Are you thinking about different acceleration because they all have different masses? Right? Let's think about reality. They all share the same acceleration. So this is the case where this is the reason why I drew you the earlier picture. So you would consider this as a 3-block system with a total mass of 6 kilograms. And that's how you know all 3 blocks will share the same acceleration, and that acceleration will be 2 meters per second square. Okay? Now, I would need you to do something here. That is, can you find out the net force, which is M times A, right? For the first block, the net force for the second block, and the net force for the third block. Okay, the 1 kilogram, 2 kilogram block, and the 3 kilogram block. Okay, can you find out the net force individually using mass times acceleration? Okay, so pretty easy calculation, I hope. All right, so the net force for the first one would be 2 newtons. The second one would be 4, and the third one would be 6. And if you add them all up, it will be 12. Are you surprised that it's equal to 12? That's the total, right, that we applied. So what you think, what you could think is like, oh yeah, I applied 12 newtons of force. And these 12 newtons of force will be distributed throughout these 3 objects proportionally. Okay? And now this is where we would draw our free body diagram for each particular force. Now, let's start off with the first one. It is true that we applied a 12 Newton force on the first object, right? But the net force is 2. Well, how come? That means there must be a force going in which direction? To the left. And what's the magnitude of that force? 10. What is this force? Not friction. This is the force of block number 2 pushing back on block number 1, the action-reaction pair. And that would also be the same force that pushes from the first block to the second block. So I hope you understand my labeling right here. The subscript 2, 1 means from 2 to 1, and 1, 2 means from 1 to 2. So that's how we have a net force of 2 newtons. Okay, and that's how we carry forward with our second diagram. So we know there's a force going to the right. The first box is pushing 10 newtons to the right, but the net force is only 4. That means we have an arrow going to the left for a magnitude of 6 newtons. And this is a force from the third block pushing the second block. And of course, the second block is pushing the third block with a force of 6 newtons. And that's the net force on the third block. Now, I find this kind of question pretty challenging to understand at the very beginning, because with multiple objects together, like, think about how you answer the question of, do they share the same acceleration or not? That already tripped up a lot of people. Okay? And then to draw these these free body diagrams and to understand net forces, that is going to be very challenging. But I hope you understand how we have the Newton's second law, the F is going to ma, and the Newton's third law, which is the action-reaction pair. That if this box number 1, the block number 1 is pushing onto block number 2, then block number 2 is pushing back on block number 1. And that's how we complete our force diagram, or the free body diagram. Okay?